Good afternoon. Welcome to Chip.Fail, Glitching the Silicon of the Connected World. This is Lagoon JKL, and our speakers are Josh Datko and Thomas Roth.
Thank you. Hello. Welcome to Chip.Fail. So to get started, who are we? So we're a team of 3 persons. Unfortunately, only 2 of us can be here today. We have Dimitri Nedospasov, who has a PhD in chip security. We have Josh Datko and myself, Thomas Roth. And yeah, before we start, we have some special thanks to Colin O'Flynn, who helped us out with a ton of questions on the details and really on what are we doing. He's a hardware blockchain expert. You should totally check out his talk later today. He's also an author of Circuit Seller, so if you want to get your copy signed, he'll be happy to do it for you. And he's also the builder of the Chip Whisperer, which is a wonderful device for glitching, for differential power analysis, and so on. In this talk, we want to give you 3 core takeaways. First off, glitching is easier than you think. So 9 months ago, I never glitched a chip, and now we've glitched a couple of them. And you really don't need to know much about hardware. It's really easy to do if you get the basics down. And it can also become part of your software and hardware development lifecycle. You don't need to rely on other people to tell you whether your chip is susceptible to glitching, but we want to show you how you can do it yourself and how you can do it yourself cheaply. Yeah, why are we here? So we all do a lot of hardware and software security consulting, and we seldomly see chips being considered as part of the threat model. And if we talk about the threat of glitching, a lot of people seem to think that glitching is magic and that it's really hard to do and that it's not a realistic attack scenario. And we want to change this. We want to make it more accessible. We want to really show how easy it is to do. And why is this getting more important and why is this interesting? Well, you can basically apply the Java methodology of hack once and break in everywhere. If you manage to break a single chip, you can break any device that's based on this chip, and you basically have a general O-Day that is unfixable without a new hardware revision. We also think that secure IoT devices are essential for a lot of use cases, and so we want to see chip vendors and also developers improve their protections against glitching. And also, as you will see, even chips that claim they are very secure might not be as secure as you would want them to be. So to start off, what is fault injection? So fault injection is a term mainly used by professionals. We in the hacker community just call it glitching. And the idea behind glitching is you basically introduce faults into your chip. So for example, you cut the power for a very, very short amount of time and see how the chip behaves. You change the period of the clock signal, or if you're Colin, you start injecting electromagnetic shocks, basically pointing a taser at your processor. What we'll talk about today is mainly voltage glitching. And so the idea behind voltage glitching is that we cut the power to the chip for a very, very short amount of time and at a very, very precisely timed moment. And this can cause undefined behavior. And so for example, if you look at the data sheet of a chip, it defines the safe operating area in which you basically see, oh, the chip is stable in these conditions. But what happens if we go beyond these conditions and start doing some interesting stuff? So for example, we could, as shown on this video, introduce a very short drop in the power pulse. And this can cause a lot of strange behavior. And so just to summarize, the basic idea behind glitching is you wait for a trigger event, you wait for a certain delay, and then you run your glitch, and then you hope to do something interesting. So for example, if you do this on a device, you might trigger on-device boot, you wait until you're right in the bootloader, you glitch during the firmware validation check, and you might be able to boot a modified firmware. And some very susceptible parts in a chip are, for example, flash reads. Basically, if you read flash data, it takes a lot of power in the chip, and we can interrupt this power. And if that happens, we basically get back undefined or garbled data. So for example, here we have a power trace of a boot up of a chip. Basically, this area is where the Bootrom, the code that is embedded in the chip, is ran. And we can see there's a huge power spike where the flash loads start. And we can do the same with RAM. So let's, for example, say we have a bootloader that has a method we call to check whether the firmware that is on the device is valid. And then we have a simple Boolean check. If firmware is valid, then we boot our firmware. But if we manage to insert a glitch right at this check, if we manage to flip a single bit, the Boolean condition will evaluate to true, and suddenly we are able to boot, for example, a compromised firmware. So yeah, how do you actually do this? My colleague Josh is going to walk you through it.
All right, so we're going to talk about the 3 steps to success. So what are the 3 methods that we have to do to apply the method of looking at a new target and getting ready? Well, there's always a prepare step, so that's step number 1. Then we have to write some firmware. So unfortunately, if you're a hardware person, this is the part you don't like, or if you're a firmware person, this is what you like to do. But we have to write some firmware. And then we hook it up and glitch it. So part 1, prepping the device. So in this part, we have to do some research about the target that we're interested in. And we have to read the data sheet and get some information. Specifically for voltage glitching, we're very interested in how the power domains are set up. And most modern microcontrollers are going to have multiple different voltages, especially as they migrate into systems on chip and get more complicated. For example, there could be a main VCC at 3.3 volts. That also could be the main logic I/O, so that also could be at 3.3 volts. However, the CPU core and the logic for the CPU may run at a lower voltage, 0.7 to 1.2 volts. And depending on the chip, that may either be fed in externally or it's internally regulated. Lastly, if there's a radio, like Wi-Fi or Bluetooth or something, that may require a different voltage. So all of this is, we are just doing this reconnaissance, trying to gather information about the chip we're trying to understand the power domains. So if we look at the data sheet, we may see something like this. This is the NRF, I believe, and NRF52, which is a popular Bluetooth chip found in many IoT devices. And this is just a diagram explaining how some of the internal power circuitry works. And this is really useful because we are going to need this information to help build out the glitcher. So let's make block diagrams, because block diagrams are fun. And so let's take the microcontroller, and we were kind of using this example of a CPU core, Wi-Fi, IP block, and GPIO. We have these 3 voltages. In this hypothetical example, right now they're being fed by 3.3, but internally they're doing different things. And that makes a difference because, well, internally we may want to be glitching different parts of the logic. So could be this core regulator that comes in from 3.3 to feed the CPU core. There could be also a different voltage regulator to drop the voltage down to 1.3. And so we're just kind of building out the block diagram here. And so then also 3.3 might just have no regulator because it's going right to the GPIO IP block. So that's all useful information. Now we know how, and we have a hypothesis of how the internal IP voltage and power systems work. Let's now look externally. So externally the chip, we have this capacitor, and so those 2 lines there on that thing is just the electrical symbol for capacitor. And it's external to the chip, and this is often recommended by microcontrollers if you look in the reference design, and because what this external capacitor does is, to use the software example, if you are familiar with databases, you've got MongoDB, but that's really expensive to go talk to MongoDB. So what do you need from that? Obviously you need memcached. So memcache acts as this little cache that's quicker to access than going always back to Mongo. Kind of a similar idea with external capacitors. You could go all the way back to the power source and get that voltage, but if you have that external capacitor there, it kind of acts like a little bit of a cache. And so if you take those external capacitors off, it's stable. I mean, we're getting 3.3 volts, but it's very fuzzy. And so that very fuzzy signal is indicative that there's lots of ripple in the power supply. This is a fact we're going to exploit when we do the glitch, but this isn't what, if you're trying to build something, this is really not what you want. You want the capacitor there to get a nice clean 3.3 signal trace. So for glitching though, get rid of those caps. Now the other thing that's interesting is, we've done our reconnaissance, we've looked at this data sheet, we're trying to glitch the logic. what's nice about this block diagram is that that logic pin that's coming out external to a capacitor, that bypasses this core regulator. And so what's really nice is when we remove that capacitor, take it out of place, we can potentially access that voltage to that logic core directly. And so that's going to be very useful for us later on. And so sometimes this is called VDD core. There could be different names on the data sheet, but the key insight here is that we have a nice direct access to the internal CPU core. We don't have to provide just 3.3, because that voltage regulator is kind of in the way. It's going to be messing things up. And now we can supply voltage directly to the CPU core. So we're sticking with the NRF example. This is just the NRF52 on kind of a breakout board in a slightly productized form. And this is, again, we've looked at the data sheet. The method is look at the data sheet, get some information. We know there's external capacitors that we may want to remove to get better access. So all those things in red are those external capacitors. They're in the way. We want to get rid of those. However, this is the point where trying to do a glitch attack is also, I should say, more art than science. There's a lot of factors that can cause an issue, one of which is if the manufacturer is recommending that you add capacitors to make your system be more stable, removing them makes them more unstable. Some chips may not boot without them. So kind of depends on the chip. But yeah, if you take those out, it may not run stable. However, so for VDE core, we can overcome this and we can provide a nice clean VDE core directly with an external power supply. So we're big fans of these cheap programmable external power supplies. You basically cut a wall wart, you wire it up, and then you've got a nice custom wall power supply, and there's even open firmware for this, and it has a serial interface if you dig around, and you can control it externally. So relatively cheap and super fun if you need extra volt power supply. So this is kind of our go-to power supply. And yeah, so the insight then again is we don't want to glitch 3.3 for this microcontroller because that core regulator is in the way. That regulator is going to be fighting the glitch. We want to go directly to the logic core because that's mainly where the interesting things are happening. So we provide that external voltage, and that's where we can glitch. And if you look, this is basically, we took this board, removed the capacitor, soldered a wire, and now we're directly where we want to be. We've got tapped to the VDE core in this case. And yeah, so this is basically, that's all the prep that you have to do. So it's a lot of paperwork. There's a lot of reading the paperwork. It's a lot of learning about the chip, but the actual physical hands-on prep for this one was just once you have figured out where that is, remove the capacitors, add the wire. Okay, so this is now we're going to be talking about what's the test firmware that we have to write. And so this is not unlike traditional embedded development where we have to do a system bring up. So it's very dependent on the manufacturer of the chip, and this is where it's either super easy if someone else has done it and you copy the project, win, or you actually have to download the vendor's SDK and then figure out why that doesn't compile, and then fight through lots of problems of why you can't get the Blinky to work. So, but basically, we're trying to keep the firmware very simple. We really just want to initialize the system. We need to provide a good, clean trigger for the glitcher to work. And we need to also know when we're done. So, what does this look like when we build this firmware? So, if we kind of think about an Arduino example, so our Arduino is a nice, simple API. It's pretty clear. And here we're going to walk through what basically this example firmware, and this is all you would need to write for a test target or something similar. So the device has to boot. So the boot ROM is going to take care of that for us, and then it's going to launch user code. And then once we get into user space, we have to do things like perhaps configure clocks. So whatever clock speed we want to write, enable or disable the brownout detector, configure some pins, and here we're setting these 2 pins to be output. Then we have to set the pin to trigger as a high. So in the kind of, where we're at is we're kind of talking about generic approach to glitching a chip. And in this stage, we're talking about making just kind of the generic firmware And so to make it easy on ourselves, we just toggle a GPIO high, and we can, that's a nice clean trigger for any system, and that's exactly what we do. Then, what it is that, to get this indicator of success, what we're looking at is we're looking at a flash read. And so we're going to be talking, that's interesting because there's code there, and there could be secrets there. And so we're particularly interested to see if our glitch affected a flash read. So basically what we do is we loop. We have something known in the flash. That could be data that you stuck in there. It could be some of the code. Somehow you know what's in what the flash read should be. And we just loop around. And then eventually, when we're going to apply the glitch, if it's not what it's expected, we win, right? So the glitch was successful. You would expect a microcontroller to always consistently read the same thing from flash, right? So you would think this, shouldn't exit, but it does when we apply a glitch. And so what does this look like on an oscilloscope? And so this is just an example. These are the two traces of those two GPIO pins we were previously talking about. And let's just go through those steps of what you would expect to see on an oscilloscope, which is very helpful when you're trying to do this kind of attack. So you start off, the microcontroller has booted. Now in this section, it's preparing the system clocks, doing all that system bring up stuff that we just have to do in order to run our code. So here's where the more interesting bits start. We have to trigger the event for the glitcher. So this is just, we artificially, in this case, made it the GPIO high. On a real target, this could be something else. And then there's one of the key parameters in the glitcher is how much to delay, right? So we're trying to glitch that flash read that happened in that loop. So the glitcher takes this, as Thomas mentioned, there's this programmable delay that we can take, and this is what we see in the next scope trace. Then we insert the glitch. And so this is where we're hoping that we get that exact precise moment to trigger the glitch, or to insert the glitch. And what happens? Well, that depends on what your indicator of success was. So in this case, so that could be, we've got another GPIO signal, we've broken out, something happened on serial, but however you set up that system, that's the indicator. And so, yeah, part 3 of this is talking about, what is the glitcher that we made? Okay, so the Chip.Fail glitcher consists of mainly 3 main components. There is this FPGA, and so we were using the Digilent Cmod A7, so it's just an RTX FPGA. It's about $70 US. It's has one PMOD connector, has a nice USB UART, pretty small. We need the other component that we're using, as we were talking about, there's lots of signals. We want to be able to drop the voltage. So there's a couple different techniques for that. The thing that we're using is an analog switch or a multiplexer, and that's what the middle board is. So that multiplexer costs about $1.80 in single quantity, and that goes on the PMOD connector there. And then we need that DPS 3003 power supply, which is about 20 bucks. And that's going to help feed in the voltages that we want. And so, yeah, the nice things about using an FPGA is we get super precise timing down to the, so we can control individual clock cycles, which is, we get that clock cycle precision running at 100 megahertz. And yeah, part of this, as we're going to be releasing the Verilog for this project as well. And so the PMOD specifically is using the Max 4619. It's a 3-channel analog switch, and it has a nice PMOD. It has a nice, it's a standard PMOD header on one end. On the other jumper is a standard 0.1-inch header, easy for breadboarding. We do have PCBs with us, so I brought, I don't know, like 200 or something. So if you see me afterwards, we'll happily give you a PCB. And this is, now we're just, what is this analog switch? For those that are unfamiliar with how this works. Basically, so there's 3 channels. Right now we're just talking about one channel, channel X. And so for any channel X, that being the output, there could be 2 different inputs. So typically, our inputs are usually some voltage level and ground. So X0 would be 1.2 volts for a VDD core, X1 will be ground. And what we want to do is switch between them. And so the way that works with an analog switch is you apply power, or it's also called the enable signal, and it'll switch over. And so it's a 3-channel, so all that is, when you do that in 3 channels, is it looks like this. And so now there's a lot of wires going on there, but it's 1 channel multiplied. And yeah, that power supply we talked about, mainly we're using it to supply VDD core. Like I said, controlled by UART, which is super nice. You can get them on Amazon. And when you hook up all this together, you have the FPGA, so we're using that as the main. So there's a host software that's driving this with Python, talking to the FPGA over UART. And then it has the trigger pin to know when to trigger the glitch. It has the success indicator, and so that depends on what the particular target is. We have the power enable signal going to the mux to switch between the 2 voltages. There's also the glitch enable signal that is doing the same thing into VDD core, and all of that's going to your device under test. And yeah, so we're going to put this all together. And I've since wasn't a big believer in 3D modeling things first, because it's like, make the PCB, get everything hooked up, then see what it looks like afterwards. Sometimes I'm starting to learn that it's useful to do 3D modeling before, because sometimes you have some fails, like when you have the PMOD and the glitcher, now you have to stack them vertically and it kind of sticks up like a nice L connector. So pro tip, 3D model, it's getting easier with lots of different CAD tools. You'll save embarrassment on slides. And now we're ready to glitch.
Awesome. Yeah, so thanks, Josh. So now that we know all the components that are involved in glitching a board, let's actually go about doing it. So as said, for the FPGA, we need a bitstream, which is basically the firmware of an FPGA. And our FPGA Bitstream provides a very simple serial interface that lets you adjust the settings, such as the pulse width, the power reset, the delay between the trigger and the glitch, and also some other options, such as whether you want to power cycle the device on every glitch attempt. And inspired by the new Chip Whisperer, we actually built a full control library in Jupyter Notebook. So this is super easy to use, and it's basically self-documenting. So you just open the Jupyter Notebook, you configure the serial port, and then you can write a really, really simple glitching software in like, 20 lines of code. And basically all you have to do to configure the glitcher is you set a power pulse, which is basically how long do you need to cut the power to fully power off the device. Because sometimes you will get stuck and you need to reboot it and so on. Then we basically just have a success indicator. We iterate over a delay range. So for example, the key to glitching is trying a million different delays, trying a million different pulse width and so on. And you can automate this really easy in a couple of lines. You just do a loop between delay from and delay to. You send the command to set that delay to the glitching board. We just have a success indicator to break later on. And then we just iterate over a range of pulses. And so basically what this does is it sets how long is the glitch pulse actually active. And this varies massively depending on your target. So for example, if your chip is running really, really quickly at 100 megahertz, you want this to be really, really short. But if you're targeting a slower chip, such as one that we will see later, this can be also a really, really long value. And then you basically just send a glitch command to the board. You wait a couple of minutes. And then you, for example, in this case, we just check the status of the GPIOs, whether our success pin went high. And if it did, we print a nice success message, and that's it. So how does this look in action? So once you found some good values, this is how the glitcher runs. So you basically just hit run on the Jupyter Notebook, and you can see the progress bar indicating the range of the pulse we are in. And on top of that is the delay. And in this case, we can see that with just roughly 200 attempts, we successfully glitched the chip. And that's really all it took. So you basically take the FPGA, you take a multiplexer, you hook it all up into Python, and you're ready to glitch. No magic, no expensive equipment. It's really, really trivial. And so let's test this on real targets. Our goals for this were basically to find targets that are commonly used in IoT devices, because we think this is where most of the new security issues will be happening. And it should be a modern chip. It shouldn't be a 10-year-old chip that doesn't have any protections anyway, and we wanted to test many different vendors that we commonly see. And so we went down to the list of 4 main targets. So the first one is the nRF52840, which is a chip that is very commonly used in Bluetooth devices, wearables, and so on. So for example, something like a dash button might use it. Then we have the ESP32, which is a super common Wi-Fi and Bluetooth chip. We have the SEM-L11, which is a high security microcontroller. And then the STM32F2 and others from the series. And our goals for this were to configure the chips in real-world conditions and just identify whether a chip is susceptible to glitching attacks. So the idea is not to necessarily have a full exploit for all chips, but just to give a very simple way of checking whether the chip you are going to use in your product is susceptible to glitching or not. And we also want to be able to test the chips in situ. So for example, we just order a basic development board, solder off some capacitors, and then we go ahead and glitch it without having to design a custom board, without having to solder a lot of stuff. All you need is a hot air gun and a soldering iron, and that's it. So let's start with the Nordic nRF52840. So for this one, we basically use the Maker Diary micro dev kit, which is pretty nice because you get everything breadboardable, and it's very commonly used in small IoT sensors. And in this case, as we've seen earlier, the target preparation that we need to do is really just remove a couple of capacitors. So in this case, it's just these 6. Add a crude jumper wire, and now we're ready to glitch. And so what we did is we wrote a very simple test firmware that does what we saw earlier. Basically, you boot the chip, it puts a trigger line high, and then we glitch a flash read, and we check if we are successful. And in this case, on the nRF52, we were successful. After 1.5 hours, we had a successful glitch attack. We were able to glitch application code, and we managed to get this glitch attempt really stable at roughly 100 attempts for a successful glitch. We tested this against a couple of demo firmwares, and we were able to find some critical vulnerabilities in a very short amount of time using this. And yeah, very trivial to do, and we'll release both the schematic to do this and also the test firmware on our GitHub, I guess later this week. The next one that I think is really interesting is the ESP32, because this CPU is really fast. So compared to our FPGA, which runs at 100 megahertz, this chip can run at 160 to 240 megahertz. And it has Bluetooth and Wi-Fi, and it's very, very commonly found in new IoT products. So for example, we had multiple customers who used this chip and who used the secure boot features of this chip. And so this was a really interesting target to us. And so, as we've mentioned before, we need to find out which power rails do we need to attack. So all you need to do is you look into the data sheet and you find the embedded power supply, and you see that there are a couple of caps you need to remove. And unfortunately, in the case of the ESP32, you also need to get rid of this tin can, and you can see that I kind of messed up the board while doing it and just soldered on some magnet wires to the V-core parts right here. And yeah, and we are ready to go basically to write our test firmware. In the case of the ESP32, we actually decided to write the test firmware in Arduino because it's really simple and it allows you to really simply select different clock speeds. And you can see our sketch for just testing the glitch is like 30 lines or so. And we basically just do a flash read on an address where we know the value. And then once that value changes, we set up a success pin and can measure it with our glitch. And to drive the board, we put it in one of those nice programmer boards which provide the 3.3 volts needed for the chip and allow us to really easily also switch out chips after we broke them, because sometimes you will break chips during doing this. So yeah. Oops, sorry. In this case, we got our first successful attack after 3 hours. And so this was a day where we managed to glitch 3 different chips in a single day, which is really amazing because it takes no time to set up. It takes no time to try anything because it will just run on its own. We slightly had to adjust the test firmware because basically the ESP takes a very long time to boot up. And so we needed to have an endless loop where we always push up the trigger, and we couldn't just reboot it on every test. So we had to adjust the test logic a bit, but you will see that in the Jupyter Notebooks we'll be releasing for the ESP. And we got this ESP32 stable within roughly 10,000 attempts. And this has some interesting impact, especially when you look at the secure boot features of the chip. So this chip I'm super excited about, the microchip SAM-L11. So this chip is a world-class, ultra-low-power MCU for IoT and security. And it's so secure, it literally won the best contribution to IoT security. And if you just search for the word secure on the website, you will find 57 hits. So this chip is 57 times more secure than some of the other chips. And if we read the data sheet, one of the things that really set us off was basically there's a factory calibrated brownout detector on VDD core. And so the idea behind the brownout detector is it detects issues on the power lines. And so for example, if your voltage drops too low, the brownout detector will, for example, reboot your chip or reset your device or whatever. And so we were kind of curious whether we can glitch it. And it was very surprising because at the first time we thought we actually messed it up because we had success literally after 5 minutes. So it's super susceptible to voltage glitching. It's it's a secure chip, and what's an issue for us is basically we have customers coming to us that want to use this chip as an HSM, as a hardware security module besides their main chip because it touts so many security features, but then once you start looking at it, it gets really, really, really easy to bypass. And so, for example, we found a bypass of the secure reference bootloader, which runs in trust zone and basically allows you to write a validated firmware. And the disclosure of that is in progress. We hope to be able to release it soon. And some more fun stuff on this chip. And just one of the things, so just how easy is it to glitch? So I come from South Germany, and we are really, really, really cheap. So $100 for a glitcher sounds really expensive. Like, I don't know how many beers that is, but it's a lot. And so the idea was, how cheap can we get this glitch? And so we built the $5 glitcher. Basically, we take one of the cheapest microcontrollers you can find on DigiKey, an ATtiny85, the multiplexer, and you end up with roughly $3 or $4 of equipment to glitch this high security chip using a very sophisticated lab setup on a breadboard. So yeah, that's how you break a very secure trust zone enabled microcontroller for $5. And now, last but not least, the STM32F2, which we call the $1 million microcontroller. You will see why in just a moment.
Okay, so now we're going to talk about the STM32F205. So some of you may have seen our talk at Wallet.Fail. We presented this at CCC last December. And we talked about a lot of different things, mainly breaking Bitcoin hardware wallets. I promise if the word Bitcoin triggers you, you can just think smart fridge. We're not going to get into the application. So don't worry about the word cryptocurrency or Bitcoin. You can just replace that in your head, and all of this still applies. But yeah, so we did this talk. There was lots of previous work on this. There was one of the papers had not yet been released. I believe it was how to apply it all. The verifying code readout protection claims, and so that's now public. So you can go read that paper. And yeah, so let's now deep dive on the STM32. So the STM32F205 is a general purpose microcontroller. It's an ARM Cortex M3, a very popular chip for, there's lots of I/O. It's just general purpose microcontroller, can be used in all sorts of things. It's also used as one of the main reference designs for a Bitcoin cryptocurrency wallet in this product called the Trezor. So, you know, Thomas looked at the L11 and we saw this secure, 57 times secure. So we wanted to look at the data sheet for the STM32 and see how many times it mentions security. Not many times. So, I mean, this is, we got the nice frowny face trying to find the word security. And that's because this is a general purpose microcontroller. It's not meant for, it doesn't even mention security in the thing. But it does have an interesting feature of readout protection. And so, in this family of microcontrollers, this is the from the ST Micro website, there's different ones for different configurations in different Cortexes, M0 core, M3, M4. And now basically there is a Bootrom or glitch attacks for these susceptible chips in this family, and yeah, so the crosses are starting to stack up. And this one is, yeah, so, and then, yeah, the F4 would also be an interesting one to see, because that's also, that one is not yet done, but that one has like a mega flash, and is also very popular as well in the STM micro family. So we talked about previously, we have to do some research, we have to kind of figure out about the attack we want to do, and if the firmware is pretty decent, we may not be able to get an application level glitch. So a few years ago, I gave a talk at DEF CON, tried to glitch the Trezor application code, was unsuccessful. And so when we all teamed up, we knew we had to move to the Bootrom. And so the Bootrom, the only really security feature the STM32 has is this readout protection. And it's not in the main data sheet, there's this app note you have to find, but basically there's 3 levels of readout protection. Readout protection 2, so now I'm just gonna say RDP2, now we all know the acronym. RDP2 is the highest security, which means you have no access. RDP0 means full access, so least secure. And RDP1 is this kind of in-between state. And what's interesting about this particular chip is how they implemented this. So there's a specific value we're looking for, and it has to be AA for RDP0, CC for RDP2, and it's not AA or CC, and you're in RDP1. So that means if we can make that not be that value, we can downgrade from RDP2 to RDP1. And so the way to do this is basically to look at the bootloader. So we were able to dump the Bootrom, and one of the things we were interested, so we had the hypothesis, does RDP only get read on the Bootrom? And so we looked through all the code, did some reverse engineering of the Bootrom, and which is readable. We had to do some OpenOCD tricks, but then we found essentially that there was no checks found, so all these checks are only for RDP0. And so now let's take the methodology that we were showing before of how to do a glitch and kind of apply it post facto to what we did. Because when we originally did this, it was a lot of flailing around, and it took 3 months of just coordinated effort. The glitcher didn't run for 3 months, but that's much time of us 3 doing it. But now, post facto, we can make it look easy, apply the method, and you win. So, like this happens in the Bootrom. So we're interested in analyzing the Bootrom for the Bootrom glitch. So first thing that happens is a power on reset event. After the power on reset event, the microcontroller is going to go into the Bootrom, and it's going to run the code that's in the Bootrom. So that Bootrom could be doing different things depending on different pins. But after the Bootrom is done, and specifically it's going to be reading RDP, that's what we're interested in, but then it's going to launch user code. And so we know that the Bootrom is going to read RDP from this internal flash, so that's where we need to insert the glitch. So this is, we're still in that investigative phase, we're still trying to learn about the target. So what we now recommend is, before you move on to a new target, you study the boot process with an oscilloscope and figure out some timing information, because that's going to help you figure out your delay and your where to apply the pitch. So we're looking at the oscilloscope of the supply voltage on the top, an I/O pin on the bottom, and here we're just trying to measure the time to user code, which is about 1.8 milliseconds. So that's how long it takes to get booted into user code. And then we can tell that because there's lots of interesting activity, and yeah. And so here then we also have the supply voltage and a reset pin, and now we're trying to show that, yeah.
So one important part here, I apologize. So one of the most important things is the problem we had with this chip is that the power on takes different amounts of time every time you boot it. And so basically the PLLs and so on need to synchronize, and some capacitors charge up or whatever. But basically, the first 1.4 milliseconds of the boot, nothing happens, and we couldn't get a reliable trigger because it was always moving every time that the execution speed was different. But then we found out that 1.4 milliseconds roughly in the boot process, the reset pin shoots high, and we can use that as the perfect trigger of when the Bootrom starts executing. So, sorry.
All right. Thank you, Thomas. And then, for the power consumption, the technique is basically using a shunt measurement. So we have a shunt resistor to measure the power, And we're in the boot ROM. We're interested in, again, here we're looking at the reset. We're also looking at the power consumption with the shunt resistor. And we see when the boot ROM starts execution. We're also, what we're trying to find is when these flash option bytes are going to be read. And so when we look at that power trace, we see a lot more activity once the flash starts getting involved. And we can pair that up with our application execution, and now we have a nice map of where everything happens. So this is what this is how we started, right? We took the FPGA, the analog switch. Now we've seen these a few times. Here we have a debugger. That's a new component because now we're interested in reading when we have access to when RDP1's downgraded. And in this case, our target is the Trezor. And this is us inserting the glitch. So we saw an example of that before, and this was the glitch on the STM32. And we did this over about 3 months of the active glitching, different parts of the world, all actively running this glitch setup. So it was very much a team effort. Eventually, we were able to insert the glitch into the boot ROM, and we were able to connect with a debugger, and it downgraded. So we were now, even though we set RDP2, and that was set in the flash, we are now at RDP1. So the key to doing this, and the key to kind of making this applicable, is to know the parameters of the glitch. And so, so now, after working with Trezor, we're happy to release these parameters. And so these numbers are essentially clock cycles at 100 megahertz. So the delay is at 17,900 clock cycles with a pulse of 50 clock cycles. And yeah, we're going to put this up on GitHub. And this, again, this particular device was the Trezor, but it's also applicable to anything that runs an STM32F2. And we think it was pretty reliable. So we did a scatter plot of what our success looks like. And these were all the successful glitches at exactly that delay. So this is about 120 attempts, and all of them hit pretty much at the same spot. So this is a pretty reliable glitch for the STM32F2, or 205. And in this case, the application was this, again, a cryptocurrency wallet. So what do you do with that glitch when you're in RDP1? Well, you can read SRAM. Is that interesting? Depends on the application. It is interesting if you ever use SRAM, which seems to be popular on microcontrollers. So if you put secrets in there, you can read them out. If those secrets are a cryptocurrency seed, that basically equals money. And so that's as much as I'll get into cryptocurrency. Go to Wallet.Fail if you're interested in more of the exploit. We originally made this glitcher. It was very specific for the STM32. So I have some of these unpopulated PCBs with me, but this is very targeted with a socket for the STM32. And basically, after the motivation of that, we wanted to kind of generalize this, and that's what we hope to show with that methodology and how to adapt it to other platforms. And so, we've been talking about basically attacking here and glitching, and so, what can we do about it? So one thing you could do is during the design component time is just choose a component that has glitch monitors. So, if you're searching for a part, and it doesn't mention security or doesn't mention voltage protection, and if that's important to your design, you may want to look for something else. The brownout detector is not necessarily glitch defense. So brownout detector is generally there for power monitoring, not necessarily for glitching. So that, most likely is not going to save you. Other thing you consider is active tamper. Basically, don't let someone physically get access to your design, to the chip. Depending on the situation, this may or may not be applicable, but if they can't get access to the chip, it's going to be hard to insert the glitch right next to VCore. If you're building a product, you should test your design. So hopefully now we all know that it can be done very cheaply, cheap amount of components. We recommend that you test your design for glitching before you release it. And lastly, there are some tricks to write glitch-resistant software, but none of that helps if the software is burned into the boot ROM. So not much you can do there. And then we'll let Thomas take it.
Yeah. So just as a conclusion, all chips we looked at were trivially glitchable. There are some more chips that we looked at, such as the AT7D21 and so on. And they all are very trivial to glitch, basically. And it can be done really on the cheap and on the very, very cheap, as you've seen before. But also, just because a chip is glitchable does not equal an exploit. You still need to be able to get your glitch stable enough. So just because your chip is susceptible to glitches does not necessarily mean it's trivial to exploit. It just means that there's a high risk of somebody maybe being able to get a stable glitch, and that you should really have a deep look at your design and see what are your protection strategies for that chip. Releases on Chip.Fail. We'll release the firmware, or well, the Bitstream and the Verilog for the Chip.Fail glitcher, glitter in this case, oops. We'll release all the PCBs we talked about, so for the MUX, for the RT glitcher, for the Trezor, and all the target test firmware. We also will release some tools for Ghidra to make Bootrom reverse engineering much easier. Yeah, so thank you. We hope to get our website live either today or later this week. You can reach us on cryptotronics.com and leveldown.de. Thank you very much, and yeah, thank you.